All right, so get this. We're going deep on Kirigami Metasheets today.
Kirigami metasheets.
Yeah, it's pretty wild. Basically a new way to move stuff around using magnetic fields. But the really crazy part, it uses a technique
Okay.
inspired by, wait for it, paper cutting.
Paper cutting, like with scissors.
Exactly. It's called Kirigami. You know, that Japanese art with all the intricate cuts?
Okay, yeah, I've seen that. But how does that, move objects?
Well, you've been digging into the research. What's got you so interested in this tech?
I think it's the potential, honestly. The idea of moving things without actually touching them, just with magnetic fields, that's huge. Think about it. A programmable surface that can move objects around. No more clunky robots or grippers, just elegant, precise movements.
Yeah. Okay, I'm with you. So how does it actually work? I get the Kirigami part, the cutting and all.
Right.
But how does that translate to moving stuff?
So picture this. You've got this thin sheet, really flexible, made of a special kind of polymer, and it's got these tiny magnetic particles embedded all over it.
Right.
But here's the key. It's got a specific pattern of cuts, like those Kirigami designs. And those cuts aren't just for looks. They actually make the sheet super responsive to magnetic fields.
So we've got these, magnetic sheets with special cuts. But how do they actually move things? Is it...
Okay, so it's not like a simple magnet, just attracting metal.
Right.
It's way more subtle than that. It's about creating these precise movements on the sheet's surface using a magnetic field underneath. So imagine you place a magnet under the sheet. Those magnetic particles react to the field, causing sections of the sheet to, rise and fall. Almost like, waves on a pond.
Oh, I see. So instead of a flat surface, we have this kind of rippling dynamic thing.
Yeah.
But how does that actually move an object? Is it like the object just surfs on these waves?
Yeah, that's a good way to picture it. By controlling the direction and strength of the magnetic field, you can literally control the direction and height of these waves. Whoa.
Creating a programmable landscape on the sheet.
That's wild.
So you just place an object on the sheet, and these controlled ripples guide it around.
So it's not like a static magnet pulling an object. It's this, choreographed movement of the sheet itself.
Precisely. It's the sheet doing the work, not a direct magnetic pull.
That's pretty amazing.
And the speed. You won't believe it. These things can react as fast as 2 milliseconds.
2 milliseconds? That's crazy fast. I can't even blink that fast. So what kind of stuff are we talking about moving? Any size limit, weight limit?
Well, that's one of the big questions. Right now, researchers are focused on small objects and liquids. Like they've moved little pieces of glass, even tiny water droplets.
Water droplets, that's impressive. And the fact that it can handle solids and liquids, that opens up a ton of possibilities, right?
Absolutely. That versatility is a big part of why this tech is so exciting. Think about it.
Yeah.
We're manipulating things without any direct contact. No more grippers, no claws, just subtle magnetic waves. It's like magic almost.
It kind of is.
That's got to be a total game changer for, delicate materials or working in really tight spaces.
Exactly. It's a whole new way of interacting with, the physical world,
Okay, so we've covered the basics of how it works, but where can this go? We touched on delicate stuff, tight spaces, but what are the researchers really excited about?
Well, the research you've got points to some pretty amazing possibilities, like miniaturization.
Miniaturization. So making this already super small tech even tinier.
Exactly.
But what's the big deal with going smaller?
Think about manipulating things at a microscopic level.
Whoa.
We could be talking sorting individual cells, assembling tiny electronics.
Wow.
Even delivering drugs to specific cells in the body.
Okay, now I get it. That would be game-changing. But wouldn't shrinking it down that small be a massive challenge?
It's definitely not easy, but researchers are already looking at different ways to do it, like using some really advanced nanofabrication techniques to create even smaller Kirigami patterns.
So this isn't just sci-fi fantasy. This is something scientists are actively working on. What else are they looking at?
You mentioned soft robotics in your notes.
Right. Robots made of flexible organic material.
Yeah, and powered by these rippling magnetic surfaces.
So they can move to complicated spaces.
Exactly, and interact with fragile things and even adapt to their environment way better than regular robots.
So instead of those big clunky robots we usually see,
we
could have these soft adaptable machines working right alongside us. What kind of real-world uses are we talking?
Tons of possibilities. Think about surgery. Surgeons could use these soft robots for less invasive procedures, reaching places they can't get to now. Or imagine them inspecting complex machinery in tight spots, fixing things without causing more damage.
That's so different from those huge robotic arms you see in factories.
Yeah.
What about uses beyond medicine and repairs?
Well, you were also interested in manufacturing.
Right, with those big assembly lines.
Yeah, imagine those assembly lines where things are just effortlessly moved around by these magnetic surfaces. No more big, expensive robotic arms.
So no more giant single-purpose robots. We'd have these flexible surfaces that could adapt to different products and needs.
Exactly. And it's not just about making things faster. It's about opening up whole new ways to customize and personalize things. Imagine products made just for you, assembled with a level of precision and flexibility we just can't do right now.
I'm starting to see how big this could be. But let's shift gears a bit. One application you were really curious about is haptic technology.
Right. You were interested in how it could change how we interact with the digital world.
Yes. Feeling things in virtual reality, that kind of thing.
Exactly. Imagine feeling the texture of a fabric in VR, or the shape of a 3D object, or even the resistance of a surgical tool, all just by touching your phone screen or wearing a haptic glove.
So instead of just seeing and hearing the digital world,
You could actually feel it.
Yeah.
It can make virtual reality incredibly real and immersive.
Wow. So what could that mean for things like gaming or education or even therapy?
It's pretty mind-blowing. Gamers would be totally immersed, feeling the weight of a virtual sword or the impact of a hit. Students could actually explore historical objects or dissect virtual animals with realistic touch. And therapists could use it to create virtual environments for treating phobias or anxiety.
That's like we're blurring the lines between the real world and the virtual world. I mean, this stuff used to be pure science fiction. It seems like the possibilities are endless. Are there any areas where researchers are focusing their energy, or are they just exploring everything?
Well, there's definitely excitement about all the potential, but researchers are also really diving deep into some specific areas where this could have a major impact. You're especially interested in biomedical applications.
Yes, I'm really fascinated by how this could be used to improve healthcare.
Think about using Kirigami metasheets to deliver drugs or therapies to very specific spots inside the body.
So instead of affecting the whole body with a medicine, you could deliver it right to the problem area.
Exactly. Targeted treatments that minimize side effects and maximize effectiveness.
Are there other ways it could be used in medicine?
Researchers are looking at how to use this tech to manipulate cells and tissues in the lab. Imagine precisely controlling how cells move and arrange themselves to create artificial tissues or even organs for transplants.
That's getting into some really groundbreaking stuff. We're talking about potentially revolutionizing regenerative medicine.
It's a very exciting area of research that could totally change how we treat all sorts of diseases and injuries.
It's incredible to think that something as simple as combining magnets and paper cutting could lead to such huge advancements.
It really shows you the power of thinking outside the box and finding innovation in unexpected places. But it's super important to remember that this tech is still very new.
Right. We're not going to have tiny Kirigami robots doing surgery on us tomorrow. So what are some of the roadblocks researchers still need to overcome?
Yeah, like you said, no microscopic surgeons just yet. One of the biggest hurdles is getting even smaller with this tech. As we shrink things down, we hit a wall with the ways we can build them right now. I mean, trying to create those intricate Kirigami patterns on a microscopic level
Right.
that needs some seriously precise tools and methods that we just don't have yet.
It's like you're trying to fold a tiny origami crane under a microscope.
Exactly.
And I bet controlling these teeny tiny devices is a challenge too.
Oh, absolutely. When you get down to that nano level, the forces involved are super delicate. Developing controls that are both precise and reliable at that scale, that's a major hurdle.
It sounds like this is really pushing the limits of what's possible right now. What about the materials themselves? Are there limitations with the polymers and the magnetic particles?
That's another big focus. I mean, the materials have to be biocompatible if we're talking about using them inside the body.
Of course.
And they have to be tough enough to handle being used over and over again without breaking down.
Right.
So researchers are experimenting with all sorts of things, different polymers, coatings, even looking at new types of magnetic materials, trying to find the best mix of features.
So there's a ton of exciting research happening on all these different fronts.
Yeah.
But even with all these challenges, it seems like the potential benefits are just too big to ignore.
Definitely. That's the feeling among the researchers. There's this sense that this tech could really change everything, and that's a huge motivator.
So for our listeners who've been with us on this deep dive into the world of Kirigami metasheets, what's the key takeaway?
Well, we've seen how something so seemingly simple, combining magnetic fields with paper cutting,
Right.
could revolutionize so many things. Medicine, robotics, manufacturing. even how we experience the digital world.
Yeah.
It just goes to show you the power of creative thinking and finding innovation in unexpected places.
It's also a great reminder that sometimes the biggest breakthroughs come from looking at old problems in totally new ways. Who would have thought that Kirigami could be the key to manipulating objects at the micro level, or building a new generation of soft, flexible robots?
It really is a perfect example of how seemingly unrelated fields can come together to create something truly groundbreaking.
So as we wrap up this deep dive, I want to leave you with this. We've explored the incredible potential of Kirigami metasheets, but the story of this technology is just beginning. What role will it play in shaping our future? What new problems will it solve? What new challenges will it bring? The answer to those questions are in the hands of the researchers, the engineers, and yes, even curious minds like yours. So keep exploring, keep asking questions, and keep pushing the boundaries of what's possible.